The relevance of acid chlorides comes from the fact that they are very useful in organic synthesis. These compounds are too reactive with water to be found in nature, too reactive with water to be used as perfumes or in foods as flavoring agents. But they are really important in organic synthesis, and you'll see why in a moment. But if we're going to talk about these guys, we really ought to know something about naming them. Let me give you a couple examples. If you know how to name carboxylic acids, it's really simple to name acid chlorides. The systematic name for this carboxylic acid is butanoic acid. The corresponding acid chloride is named by replacing the IC and acid with YL, chloride, butanoyl chloride. It's the same thing for common names. Butyric acid loses the IC and acid and gains the YL, chloride, butyryl chloride. Benzoic acid loses the IC and acid and becomes benzoyl bromide. Notice these are two words. You use the same approach in the systematic nomenclature and the common nomenclature. Okay, we'd like to talk about the chemistry of the acid chlorides, but if we're going to talk about chemistry, we better talk about how to make these compounds. They're made directly from carboxylic acids. Again, using butyric acid as an example, the carboxylic acid is transformed directly into the acid chloride using thionyl chloride, SOCl2. This reagent may look familiar because it's used to transform primary and secondary alcohols into chlorides. In this case, like in alcohols, the hydroxyl group is replaced by chlorine. In both cases, the reaction depends on the hydroxyl group reacting with thionyl chloride to form an intermediate that makes a very good leaving group. The hydroxyl group reacts with sulfur to make a good leaving group plus a good nucleophile. So an unshared pair of electrons on chloride will act as a nucleophile to displace this leaving group, either from an intermediate derived from an alcohol or from an intermediate derived from a carboxylic acid. If it's an alcohol, the reaction is an SN2 reaction. And if it's a carboxylic acid, it's nucleophilic acyl substitution. Whether we're starting with a carboxylic acid or an alcohol, thionyl chloride gives very good yields of the desired product. Again, the key to these reactions is the fact that the intermediate has a very good leaving group formed by thionyl chloride, and we have a good nucleophile formed by the reaction with thionyl chloride. Okay, so we know how to make acid chlorides. Let's get to their reactions. I've listed here 4 key carboxylic acid derivatives: acid chlorides, acid anhydrides, esters, and amides. And I put them in an order that reflects both stability and reactivity. The acid chlorides are the least stable of the carboxylic acid derivatives, and amides are the most stable. And for that reason, the acid chlorides are the most reactive, and the amides are the least reactive. The transformations occur by nucleophilic acyl substitution, a reaction mechanism that readily transforms less stable to more stable carboxylic acid derivatives. Because acid chlorides are the least stable, they can be converted into all 3 other types of carboxylic acid derivatives I've got listed here. In fact, acid chlorides are the intermediate of choice for making acid anhydrides and often for making esters and amides. Let's look at the specific details of these reactions. Acid chlorides are converted into carboxylic acid anhydride by reaction with carboxylic acid salts. The salts are made directly from carboxylic acids using bases like sodium hydroxide. Acid chlorides are directly converted into esters by treatment with alcohols. And treatment of acid chlorides with amines converts acid chlorides directly into amides. In fact, this reaction works well when we're using ammonia, when we're using primary amines. There's 1 alkyl group attached to nitrogen. And when we're using secondary amines, there are 2 alkyl groups attached to nitrogen. So you see that we can say that acid chlorides are the gateway intermediate to making carboxylic acid derivatives. Carboxylic acids themselves are transformed into acid chlorides, and from there the acid chloride is transformed into anhydrides or esters or amides, as you wish. Synthetically, this really is a gateway intermediate. And so you see that the acid chlorides are very relevant It's the way we convert carboxylic acids into their derivatives. There are some other useful reactions of acid chlorides. Let me summarize a few. I've mentioned that acid chlorides are very sensitive to water. The reaction with water converts them into carboxylic acids. Synthetically, this is really not very useful because the acid chlorides are made from carboxylic acids. But I put the reaction up here because it's so critical. It's truly important that the reactions of acid chlorides be done under conditions that are very dry. Otherwise, you end up with carboxylic acid as product. Beyond that, here's another reaction that may look familiar. Carboxylic acids themselves are reduced with lithium aluminum hydride, and so are the acid chlorides. The carbonyl is replaced by a CH2, while the chlorine is replaced by OH. Grignard reagents react with acid chlorides, and they react twice. The first step in the reaction with the Grignard reagent forms an intermediate ketone, and the ketone reacts with the Grignard reagent as well. So we've added 2 moles of that alkyl group from the Grignard reagent. And the product here is a tertiary alcohol, while the product of reduction was a primary alcohol. And finally, if you use a different organometallic reagent, lithium dialkyl cuprates, the alkyl group is added only once. So the alkyl group replaces the chlorine and no further reaction happens. We can, at will, use a Grignard reagent to make tertiary alcohols from acid chlorides, or use a cuprate to make ketones from acid chlorides. And there's another way that acid chlorides can be used to make ketones. You might already be familiar with this reaction. When an aromatic compound like benzene or substituted benzenes is treated with an acid chloride plus aluminum chloride, aromatic ketones are formed. The 4 reactions that I've shown here, together with the conversion of acid chlorides into other carboxylic acid derivatives, summarize the important synthetic uses of acid chlorides.